Hello Year 12. It's starting to rain as I record this on Monday. Hope you're all well. This is a lesson all about terminal velocity. As always done, a little starter for you. So got two cars here, top one and bottom one. You can decide who's in the car. And you've got a forward force of 3,500 newtons, a air resistance, etc. of 2,000 newtons. And here you've got the same forward force, but this time the air resistance is 3,500 newtons. What I'd like you to do is I'd like to tell me if the forces are balanced or unbalanced. And then can you tell me what the resultant force is? And then can you tell me what's going to happen to the speed of the object? And like I've done it before, what I'd like you to do is pause the video, get out back your book, piece of paper, whatever, write down your answers, and then go back to the video again and find out you're correct. Welcome back. So on this first one here, you should have said, first of all, is the resultant force is simply going to be 1,500 newtons, and it's going to be this way. And this is going to be then an unbalanced force. He says, writing it down. And what's going to happen is the speed is going to increase. It's going to accelerate. On this one here, you should have said they are going to be balanced forces because the resultant force is going to be 0 newtons. And what should happen to the speed? Well, the speed remain the same, or it will stay constant. Therefore, it's doing 3 meters per second beforehand. It's still doing 3 meters per second beforehand. Afterwards even. Okay, so as mentioned before, all about terminal velocity. Might have to do this in 2 separate videos. I'll see how I get on. So what you need to be able to do is state the acceleration of an object falling freely under gravity. Describe the forces acting on a falling object and how these forces would affect acceleration. Explain why a falling object reached terminal velocity. And then draw a velocity time graph for a falling object. Explain the change in acceleration, including a vacuum. That sounds a lot, doesn't it? It's not too bad. Okay, now this first one is really an experiment that Galileo did many moons ago. And he took a bet on this and he won some money. I would have done it in the lab, but obviously I can't do. It's therefore, I'm going to go through it using a video. So it's called the feather and coin experiment. So here's going to be a feather, and here's going to be a coin. Well, what I've done is I've changed it to football. Why? Because apparently this is the Euro Finals 2020 football, which is sadly not happening. I know. Terrible, isn't it? Anyway, imagine I had a football and a coin, and what I can do is drop them both, and under the influence of gravity, they're both going to fall down because they have got a weight. But obviously the weight of the football is going to be a lot larger than the weight of the feather. Therefore, what Galileo did is he took cannonballs, in fact, and topped the leaning town of Pisa, and he held those, and he then had some lighter cannonballs and dropped them off. Now, in the air, if I drop these, it's pretty obvious which one is going to reach the bottom at the first. Okay? What really is quite bizarre is what happens is when you do it in a vacuum. So I'm going to quickly show you this little video, which is a Brian Cox famous video. And what he's going to do is going to show you dropping your 2 objects in a great big chamber, first of all in air, and then what he's going to do is going to drop them in a vacuum. And he says trying to find it. Watch this, it's very exciting.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
Hasn't Brian Cox got a massive pair of teeth? Anyway, yeah, basically in the air, it's pretty obvious what happens is the feather is going to reach the ground a lot later compared to the ball. Obviously, it hits the ground first compared to the feather if you're doing it in air. But the important thing I want to see is if you look at the video very carefully, if you do it in a vacuum, which means you got no air, what happens then is they both reach the ground at the same time. Now, the reason why this happens is there's one force we've not been talking about, and it's called air resistance. And it's obviously acting in an upwards direction. But in the case of the feather, because it's got a large surface area, it's got a bigger air resistance compared to the ball. And because it's got a bigger air resistance, and what happens then is the resultant force down gets affected. And therefore, because it's got a bigger air resistance acting up, this one takes a lot longer to reach the ground compared to the ball. And this is what Galileo realized. Now, what in fact he did is he took different cannonballs up, where he had small cannonballs and he had a large cannonball, say this size here, and he dropped them off the Leaning Tower of Pisa. Well, we're looking at cannonballs, because they're quite small, the air resistance doesn't take account at all. Therefore, if you've got no air resistance at all, i.e. you're doing it in a vacuum, everything will reach the ground at the same time. And the reason why that happens is because everything falls down due to gravity, and everything will accelerate at 10 meters per second squared. But as soon as you do it in air resistance, as I mentioned before, takes effect. And what the air resistance does, it slows the object down. And the air resistance of the feather is going to be a lot larger than the football. And you saw that in the video. In a vacuum, what happens then? They reach the ground at the same time. Now, where I can take this further is I can take it to the situation of where we're going here. Trying to find it is to the, oh dear, I've now lost everything now. I think I closed it down. Never mind. Going back to here, I'll find it here, is where you can start looking at terminal velocity. Now, this I will spend quite a long time in the lab doing, and we're going to have a go of showing this here. There's a way to make it bigger, I think. Is it over here? Is that bigger? It's a little bit bigger. Not much bigger. Oh, well, I'll do. Anyway, here we go. Now, it's a really, really, really good video, this. Now, what you've got here, well, simulation rather, is a velocity time graph. Okay? So I want to imagine we have the most exciting lesson of all. We've all gone up an aeroplane, and what we've done is we're going to jump out the aeroplane. Luckily, we have got a parachute attached to us, which means we're not going to die. So here we go, jump out the aeroplane, and we're just here. Now, what you've got here is that velocity time graph. Now, what I'm going to do is I'm going to jump him out the plane, okay, and pause it very quickly. When you first jump out, you have got a weight of 686 acting down, which means your speed is going to increase. And you can see here the velocity is starting to go up. First of all, because you're not moving, you haven't got any air resistance at all. You've only got the weight. But as soon as you start to move, you've got a little bit of air resistance. Now, it starts off very small, i.e. 112, and the weight is 686. Therefore, the resultant force, matter of fact here, was going to be, it's going to be 574. The resultant force acting down, which means the velocity will increase. It is unbalanced, therefore the speed will increase. But if I now start going forward in time, as you get faster and faster and faster, can you see now the air resistance is getting bigger and bigger? Therefore, the resultant force acting down is getting smaller. Therefore, the speed will start to increase, but the acceleration will start to go down. And you see here, the acceleration has gone down to 3.1. I forgot to look beforehand exactly what the acceleration was. But anyway, you can see the steepness of your velocity time graph is getting less. And remember, the steepness of the gradient gives you the acceleration. So the speed is still increasing, but the acceleration is going down. Now, eventually, as it keeps going down like this, what happens is you get faster and faster. The air resistance will get bigger, but look for this very, very special moment just here, where this, it gets bigger and bigger, the acceleration is getting less and less, and it's not quite getting there. It's going to get there eventually if it kills itself. Go on, get there. Is where you're going to get the air resistance will go up to 686. I'm trying to find it. Come on, 685. Near enough there. There you go. It's near enough. Where this one, the air resistance is now equal to the weight. now the resultant force is 0. The forces are balanced. And if they're balanced, can you see now it is flattened out, or it's plateaued, which is going to be flat here because now there is no resultant force. Guess what we call this? Terminal velocity. And believe it or not, if we all jumped out of an aeroplane, your terminal velocity is about 100 miles per hour. Now, hitting the ground at 100 miles per hour is not a good idea. So what we do is we open up a parachute. Bang. Now, I've just opened a parachute up. Therefore, now I've dramatically increased the air resistance because I've got now a great big whopping great big parachute here. And, oh, my little pad's died in me. Come back, pad. Is now I've increased the air resistance. Oh, might work, might not. I've increased the air resistance. And now they're going to have unbalanced force again. Here's my keyboard. Has died in me. So now it's going to be unbalanced. And because the forces are unbalanced, now we have acceleration. But now the acceleration has gone negative because the resultant force is upwards. Hence, the speed starts to decrease. But as the speed decreases, the upward force also decreases. So eventually now at this point here, can you see now we have balanced forces where the upwards force is equal to the downwards force. The resultant force is going to be 0. And therefore, what's going to happen now? He's going to be basically falling down a new terminal velocity, which down here is about 5 meters per second. So the one up here was about 50-ish. Okay, well, 45, 46. And now the new terminal velocity is 5 meters per second. And that's the speed which is basically acceptable to you to reach the ground. Now, I'm going to stop this video here and go into the second part. And the second part, I'll hopefully get recharge my little pad up.